Welcome back. Welcome back to my calculus videos. Today we're going to be talking about the first derivative test for local extrema. If you're following along using the same book, this is section 5.3. Let's dive right in. So in the last section, what we saw was critical points. We calculated critical points where we found the derivative of a function equal to 0 or undefined. And then we said, okay, let's figure out whether there's a maximum or a minimum happening there. And one way we could do that is by calculating values and then saying, okay, well, that one's higher than that one, so it must be a local maximum, etc. And what we're going to add today is we are going to add an analysis of whether the derivative is positive, indicating an increasing function, whether the derivative is negative, indicating a decreasing function. And then we're going to look at the fact that if we have a critical point and the derivative changes sign, then it must be either a maximum or a minimum. There's an example there that I've circled in red. You're going up, you got a critical point, then you're going down. Must be a local max. And there's two other examples on this page of the same thing. And then we'll notice that if we have a critical point, but the derivative does not change sign, going down, critical point continues to go down, then you don't have an extrema. All right, so I'm going to separate out the individual situations, and we'll talk about these a little bit more. So first of all, let's talk about a local maximum. Local maximum, we have something going up, something going down. We have the derivative equal to 0. We have a derivative greater than 0 followed by a derivative less than 0. We could also have a function going up and then going down with no derivative at the top, a corner or a cusp. So there's your possibilities for a maximum. Now let's talk about local minimum. Going down, going up, and in between a 0. Or we might have something which looks like this, where we're going down, we're going up, and in between the derivative does not exist. Again, a local minimum. Now, of course, remember, we're dealing with continuous functions only here. So if we have a non-continuous function, none of this applies. So let's look at the neither case, neither a minimum or a maximum, or neither, depending on where you're watching this video from. We're going up. We have a critical point, and then we are going up, or we could be going down, have a critical point, and afterwards continue going down. So those are your three options with examples of what each of them looks like. And let's look at a couple quick examples. So example 1, we've got a cubic function, which is x cubed minus 12x plus, minus 5. Sorry, I had my notes set off too far to the side, and now I've just bumped my camera in the meantime. Okay. Wow, this is awful. All right, there we go. Minus 5. So we know this continuous because it's a cubic. We know that it's differentiable everywhere because it is a cubic. So we will proceed from that premise. The derivative of this function is 3x squared minus 12. And doing a little bit of solving, we know that it's equal to 0 when x equals plus or minus 2. So here's a way to organize your data to make sure that you don't miss anything. and I'm going to recommend that you do this every time you're analyzing a function. I make a number line, and I mark off to the side derivative. And I could put function here if I wanted to analyze the function, because I'm going to want some values. And I could add second derivative to the bottom, which I'm not going to do right now because we're not dealing with second derivative right now. But I have just determined that there are two zeros. Now, what do I know about this first derivative function? Well, what I know is that the derivative is going to be greater than 0 when x is greater than the absolute value of 2. In other words, on the outside of the function. And what I do here is I visualize this. It's a parabola. It's going up to the left, right. It's down in the bottom. So my derivative is going to be positive out here and out here. And the derivative is going to be less than 0 when x is less than absolute value of 2. So my derivative is negative here. So immediately what I see here is that I have a local maximum at negative 2. My derivative is positive, followed by 0, followed by negative. And I have a local minimum here at positive 2. I wrote negative 2 on the screen. If that was confusing you, there you go. At positive 2, I have a local minimum because it's going down, and then it's 0, and then it's going back up again. So the last thing I want to do is I want to figure out f of 2, and f of 2 is negative 21. And I want to figure out f of negative 2, and f of negative 2 is positive 11. So I now know that I have a local maximum at 11. Negative 2 comma 11 is the point on the graph. I have a local minimum at negative 21. And now what I need to do is I need to figure out whether any of these are absolutes. Well, what happens as x goes to negative infinity? This function goes to negative infinity. It is a cubic. And as x goes to positive infinity, this function also goes to positive infinity. Again, end behavior of a cubic. I'm just looking at the x cubed value because it is the dominant function. And so what we discover is that there are no absolute extrema. There is only a maximum at negative 211 and a minimum at 2 negative 21, and they are both local. All right. Quick second example, example 2, and then we will be done with this video. Slightly more complicated function because we are going to take a composite function, x squared minus 3 times e to the x. The derivative using the product rule is 2x e to the x plus x squared minus 3 e to the x. And I'm going to go ahead and oh my gosh. I'm going to go ahead and factor out the e to the x, which gives me e to the x times x squared plus 2x minus 3. E to the x is greater than 0 for all values of x, so I don't have to worry about that. I can focus on the quadratic. I know that the quadratic is equal to 0, so the derivative is equal to 0 when x is equal to negative 3 and positive 1. I'm going to draw my number line, negative 3, positive 1, g of x, g prime of x. There are my zeros. And again, I know that there are no does not exists because I know that both of these functions are continuous and differentiable, which means that their product is continuous and differentiable. So now, a little bit tougher here. I'm going to have to play around a bit to figure out where the derivative is positive and negative. But again, I only have to deal with the quadratic. Since e to the x is always positive, I know that this derivative is going to be positive outside of negative 3 and 1. I know that it is going to be negative inside of negative 3 and 1, which means that this is a local maximum and this is a local minimum. Again, going up, followed by going down, and then going down, followed by going up. Let's talk about the end behavior very quickly. Well, my end behavior as x goes to negative infinity, e to the x is the dominant function, which means that g of x will go to 0. And as x goes to positive infinity, again, e to the x is the dominant function. G of x will go to positive infinity. So what does that mean for me? Well, I need to calculate g of x. Doing a little quick calculation, I find that g of negative 3 is 0.299, and that g of 1 is negative 5.437. So my graph looks something like this, which tells me that this is in fact a local maximum at negative 3, 0.299, and that this is an absolute minimum at negative 5.437. The graph never goes below 0 over here, and then it goes up to infinity. So we have an absolute minimum, we have a local maximum, we have no absolute maximum because the function goes to infinity. All right, thanks for watching and hope you learned something.